Hi everybody. In this talk I'm going to present recent results guides, photovoltaic and tunable light emission devices. The search for new materials, metallic nanoparticles, has grown in the last 20 years due to several applications for different technological purposes. In this context, plasmonics appeared as a new field to explain the metallic nanoparticles and their interaction with the electromagnetic radiation that creates the surface plasmon resonance, the collective oscillation of free electrons in the metal surface, and the appearance of the electric local field that surrounds the nanoparticles. When the rare earth ions are excited and positioned near this local field, the photoluminescence can be increased. However, it depends on several factors as host, distance between the rare earth ions and the metallic nanoparticles. In this talk, I will focus on the important role of metallic nanoparticles in glasses and important technological applications. Here I show you the outline of my talk. First of all, I'm going to talk about the motivation for the use of these glasses based on germanium dioxide and tellurium dioxide. Then I will show you the techniques used for glasses and thin film production. And finally, the applications: waveguides for infrared amplification, layer for silicon solar cell, white light generation and tunable light emission, and the acknowledgements.
Well, now I present the motivation for the use of these glasses. They have a large transmission window from visible to medium infrared, low melting temperature with respect to silicate phosphate glasses, high chemical stability, high refractive index, normally around 2, low cutoff photon energy that normally reduces the low non-radiative losses. They are adequate hosts for rare earth ions incorporation, metallic nanoparticles nucleation, and radiation shielding. Their enhanced linear and nonlinear optical properties showed several applications as color displays, lasers, optical amplifiers, ultra-fast response device, and cover to enhance silicon solar cell performance. The preparation of the bulk samples. First of all, we have the mixture of the reagents, then the melting, an additional annealing takes place to form the metallic nanoparticles by thermal reduction. The waveguides are produced with the sputtering technique. This technique is used to fabricate the thin films that form the core of the waveguides, where light is guided. In this case, we need targets to produce the thin films. Some of them are commercial and others are produced by us. And here I present you the methodology used to prepare the targets. In this figure, I show you the compact sputter system that is used in all of the experiments. I review results of waveguides for infrared optical amplification. One of them is co-doped with ytterbium and thulium ions to operate at 800 nanometer. The other one is co-doped with ytterbium and erbium ions to operate at the third telecommunication window, nanoparticles. Moreover, in both cases, we use the pedestal architecture. I'd like to highlight that the lack of studies regarding the pedestal architecture motivated these experiments. The pedestal architecture has advantages to the core. It is the silicon dioxide that's etched. So using the conventional microelectronics procedure in clean room, we prepare the silicon dioxide pedestal. So the first step is the preparation of the silicon dioxide pedestal, and the last one internal reflection of light due to the high contrast between the refractive indexes, 1 for the air, 2 for the core, and 1.5 for the silicon dioxide pedestal. Results can be found. Different procedures were used to produce the pedestal architecture with and without chromium mask, as is going to be shown. Here are the steps used for the pedestal prepared with chromium mask. The first pedestal was like this and presented the micromasking effect, a columnar growth due to chromium mask that was not totally removed and that compromised by reducing the chromium mask thickness and by increasing the etching steps of silicon dioxide. Then we obtained this beautiful profile with core height of about 500 nanometers, micrometers. Silicon dioxide pedestal, and the last one, Here I show you the steps used for the pedestal waveguide fabricated without chromium mask. In this case, it's used a silicon dioxide mask, and unlike the other case, silicon and silicon dioxide are both etched. The advantage can be observed in this figure. Effect. Of course, this impacts positive of the silicon dioxide pedestal, and the last one is sputting. Results of waveguides for operation at 800 nanometers are presented here. The core is fabricated with this host, co-doped with ytterbium and thulium ions, and decorated with gold nanoparticles islands. In this figure you see the inner of the sputting chamber with the two electrodes. On one of them we put the target of the ytterbium oxide fabricated by us. On the other electrode we put the target in order to reduce the rate of gold, that is the guidance. Moreover, we use a short period for gold deposition, around 3 minutes, and a low power at about 5 watts. Gold nanoparticles with diameters varying from 10 to 40 nanometers can be seen in this figure that was obtained by atomic force microscopy. Relative gain increase of about 100% was reached to the plasmonic influence of gold nanoparticles. The experimental setup used for these measurements can be seen here, where signal and pump lasers are multiplexed by a WDM. Then the signal is sent to the sample, collected by a lanced fiber with 1 micrometer diameter, to be sent to the spectrometer. A pedestal waveguide was also fabricated to operate at the third telecommunication window. It was used the same host, but co-doped with ytterbium and erbium ions, and also decorated with gold nanoparticle island. Like the other case, a similar setup was used to determine the relative gain, and in this case, a waveguide width of 6 micrometer. This increase is attributed to the presence of these gold nanoparticles with size varying from 2 to 6 nanometers. We highlight that the absence of chromium mask might have contributed for a better performance, as it was not possible to measure it again for waveguides with smaller than 30 micrometers when the chromium mask was used. I will show you a different result that was also already reported. It refers to a potential material based on these hosts, germanium dioxide and bismuth oxide, doped with thulium ions with silver nanoparticle for applications at 1.47 micrometers. In the absence of thulium, we observe a large band related to bismuth ions. A quench of this band occurs when thulium ions are added. And then we have the appearance of this band centered at 1.47 micrometers related to this transition of thulium. By adding silver nanoparticles, we observed an increase of about 50%, and this was attributed to the plasmonic effects of silver nanoparticle. The relative gain is also measured, and in this case, an increase of about 500% is observed due to silver nanoparticle, and is correlated to the photoluminescence growth. This photoluminescence growth is attributed to the local field around silver nanoparticles that increase the density of thulium ions that are excited. The experimental setup used to determine the relative gain can be seen here, where signal and pump lasers are overlapped by a beam splitter. Then the signal is sent to the sample and collected by a spectrometer. I'm going to show different results of glasses used as cover layer to enhance the efficiency of silicon solar cell. As there is always a mismatch between the solar spectrum and the silicon solar cell absorption, a way to overcome this problem is based on covering the solar cell with a luminescent material that makes use of the down or of the up conversion process. Then I will show 3 different results that were also already reported. Motivated by this one, in which photoluminescence increase of 100% of European ions at 614 nanometers was observed due to the addition of silver nanoparticles, we decided to use this material that is prepared with this host, tellurium dioxide and zinc oxide. The experimental setup can be seen here, and in order to reduce the reflection losses due to the high contrast between the refractive index, 2 for the glass and around 4 for the silicon solar cell, we used a matching oil with refractive index of 1.5. Using the electropyrometers current and voltage for maximum power, we determine the efficiency for different cases. For the uncovered solar cell, for the solar cell covered the matrix doped with europium ions, and covered the matrix doped with europium ions and silver nanoparticle. And the largest increase is obtained in this case of about 13% for the sample prepared with silver nanoparticles in accordance with the photoluminescence results. Here is another result. In this case, we used a different host based on tellurium dioxide, germanium dioxide, and lead oxide, and different concentrations of rare earth ions were also used. This figure presents results of the crystalline planes of silver nanoparticles and were obtained by transmission electron microscopy. The influence of the rare earth ions can be seen here, and the influence of silver nanoparticles can be seen in these 2 figures. We highlight the large increase, the large photoluminescence increase for the sample prepared with 5 wave% of europium with respect to the one with 1 wave% of europium. However, regarding the efficiency increase, we observed similar results as can be seen in this table. And this can be attributed to the larger transparency of the sample prepared with 1 wave% of europium with respect to the one with 5 wave% of europium. So not only the luminescence but also the transmittance play an important role to optimize the silicon solar cell performance. This last example shows us the role of samples doped with europium ions with titanium nanoparticles crystallized in anatase phase, as can be seen in this figure that exhibit electron diffraction results that show the polycrystalline diffraction rings associated to anatase. Photoluminescence increase of about 60% was observed due to europium ions located in the low symmetry size of titanium nanoparticles. We highlight that annealing at 400 centigrade degrees favors phase transformation from amorphous to anatase phase. Increase of the silicon solar cell efficiency was of 16%, and it was attributed to the presence of titanium nanoparticles in anatase phase. This proof of concept results show the possibility to use metallic or dielectric crystalline nanoparticles in order to improve silicon solar cell performance. Moreover, this method can be extended to different cover layers and other photovoltaic devices, organic or inorganic solar cells. White light generation and tunable light emission influenced by silver nanoparticles hosted by triply doped glasses were also reported. In this case, we could see two different things: white light generation controlled by silver nanoparticles and color change controlled by different silver nanoparticles concentration. A strong white light generation was obtained by adjusting the adequate concentration of rare earth ions and silver nanoparticles. On the other hand, using a different concentration of rare earth ions, keeping them fixed, and varying the concentration of silver nanoparticles, two different things could be observed: tunable from white light to green light, and tunable from white light to green yellow. These results show the potential of these materials for different applications as displays, solar cell, or any devices that need tunable visible light emission. Thinking about the future, well, we can think about new architecture for the waveguides with the use of the nanolithography process. We can think about random lasers using metal-dielectric nanocomposites based on Germanium and Tellurite glasses with and without metallic nanoparticles. You can think about transparent glass ceramics with rare earth ions and metallic nanoparticles. We can study the influence of silver nanoclusters on rare earth ions doped glasses based on germanium dioxide, viewing white light generation and tunable visible light emission. We can also use these materials for nuclear radiation shielding. I'd like to acknowledge the National Institute of Photonics, the National Laboratory of Nanotechnology for the use of the transmission electron microscope. I'd like to thank the Polytechnic School of University of São Paulo for the use of the clean room to prepare the silicon dioxide pedestal, and I also thank my collaborators from all these institutions. I thank you all for your attention.